We're going to talk about electric potential today. And first, though, I'd like to review with you what an electric field is, and then review a couple of old concepts. It's been a while since we dealt with work and gravitational potential energy. These ideas will help you understand what electric potential energy and what electric potential difference is. We're also going to define what voltage is, and voltage is measured in volts. And then we'll talk about equipotential. What do we mean when we use the word equipotential? I'll define that for you. Okay, so let's start by reviewing what is an electric field. Electric fields. Electric fields are what you get when you separate charge. You put a bunch of positive charge somewhere, and somewhere out in the universe is an equal amount of negative charge. And you don't even have to see them, but if you have a little test charge, if you have an object with charge that's in between these guys, you're going to feel a force, an electric force on this guy. Let's say this guy has a charge of Q0. This guy feels a force of F. And we say that the field around it, that is the space around these separated charges, can apply forces to objects that are placed in that space as long as they have a net charge on them, and that the electric field describes how much force this object is going to feel depending on how much charge it has. So we say the electric field, and we use the capital letter E, by definition is equal to the electric force that's felt divided by this charge right here, divided by Q0. And so this was the definition of electric field, and of course it had units of newtons per coulomb. We also drew electric field lines, didn't we? We said if I put my test charge here, it'll get forced this way, and then we can connect all those force vectors together. It might get kind of curved like this, and I think we had some rules for those electric field lines. We said that electric field lines always start at positive charge, they end at negative charge. And the direction of these arrows indicates the direction of the force that a positive test charge would feel. We define the direction of the electric field by what it does to a positive test charge. Okay, but in any case, this is really our definition for the electric field. Now let's review what we meant by work. Remember that work is a transfer of energy from one object or one system into another by using a force. And so the example that I usually use here is if I have a little car and someone is applying an outside force to it, and that object displaces through a certain displacement, a certain distance here in this direction, that the work, that somebody somewhere has energy, and they're transferring energy into this little car, and that car, maybe it has a mass of m, it's going to be kinetic energy. But maybe the force that you're applying isn't making it go faster and faster. Maybe the work that you're doing is going to make it go higher and higher. So here's my force that I'm applying. Of course, gravity is pulling it down, but if we lift this thing up, I'm doing work against gravity, and I am lifting at a certain height. But the calculation for work is the force that I apply times the displacement. I'll call it delta. Well, in this case, it was a delta x. In this case, it's a delta y, or an h. So I'll just say delta r, because r can be in any direction. And then remember that the amount of work done depended on these two vectors being parallel to each other. So this tells you how parallel they are. You multiply by the cosine of the angle between the force and the displacement. And in these cases, the angle was 0 degrees, right? Here our force and our displacement's in the same direction. Here I'm applying a force up and I'm displacing up. So the angle between the force and the displacements is 0. The cosine of 0 is what? It's 1. Okay, and then these have units of newtons times a meter. That was called a joule. So work is when I apply a force through a displacement, and the direction matters. But remember that work itself is a scalar. Work doesn't have a direction associated with it. If you have 10 joules, if you've done 10 joules of work, you don't say 10 joules of work to the east. You don't give a direction to it. It's a scalar. Okay, and finally, let's review gravitational potential energy, which we called U sub g, right? And U sub g is very much related to what we were talking about up here. Gravitational potential energy is the amount of work that gravity can do when you bring something to a reference. So if I put a rock or something like this, it has a mass, right? Gravity is pulling down on it, right? Here's the force of gravity. And of course, this is going to go down some distance, delta y, right? It's going to fall down. And we say that gravitational potential energy is the work that gravity can do to bring an object from where it starts to whatever reference you pick. Here, usually we pick the ground, right? Here's the ground. And so we would say, well, the work that gravity can do, okay, the work done by gravity is equal to, well, in this case, what is this force of gravity? It's the mass times the gravitational field times delta y. But delta y really is my height above the reference, so we usually call that h. So U sub g equals mgh. Now the reason I'm reviewing gravity is that gravity is a really good way of visualizing what's happening when you have an electric field instead of a gravitational field. Look, this object has a force on it because it has mass and it's in a gravitational field. And if you're close to the Earth's surface, that gravitational field is 9.8 newtons of force per kilogram of mass. Well, now we're going to take these ideas and extend them into what happens if I put an object that has charge on it, a net charge, in an electric field. And we're going to ask ourselves, how much work can that electric field do to the object? And we're going to call that electric potential energy. And then we're going to divide it by the charge on that object, and we'll call that electric potential. So let's go ahead and get to that. One of the things, I think the easiest way to explain this is to start off with a uniform electric field. So you can do that by getting two plates of metal and hooking a battery up between them so that the battery will force positive charge on one plate and negative charge on the other. So here we're going to, let's put a title on this. This is going to be electric potential. Now, we have separated charge. And what happens when you put one on a plate, on a metal plate over here, and I draw a metal plate as a line, but that's just because I'm looking at this metal plate in cross-section. Okay, and it just makes it easier to draw. Just think of this as being in cross-section of a metal plate that's got positive charge on it, and over here it's got negative charge. And you know, remember the rules for electric field lines. You get a little bit of a bulge out here, but the electric field in here, I'm not drawing it very well, am I? If we just pretend like, let's not worry about these edges, let's just do this, that this electric field is everywhere the same between these plates. If you get two plates of metal and you charge one with positive and the other with negative, and you bring them pretty close together, in between you get a uniform electric field. And on the outside, out here, there is almost no measurable electric field. And there's no measurable electric field out here. It's all in between the two charges. That's different than the electric field that we did with point charges earlier. But in any case, if I put, let's put a little positive test charge right. Well, let's just put it in the middle. And I'm going to give it a charge Q. This thing's going to feel a force, isn't it? And what is that force? Okay, well, here's that force that's acting on this charge. Well, that force is going to be equal to the charge on this object times the electric field that this thing is immersed in. Now you might think, oh, whoa, I don't get that. But think about gravity. What is the force of gravity? The force of gravity is equal to m, an object's mass, times g. Well, g is the gravitational field, right? 9.8 newtons of force per kilogram of mass near the Earth's surface. So here we're just kind of doing the same thing to figure out what this electric force is. The electric force is just going to be how strong the electric field is times the charge. Okay, well, so if I have the charge here, you know, how much, let's think about this for a second. Do you see that, what if I were to let this thing go? What would happen to it? If I were to, you know, let's say I'm holding the charge like this. I'm holding it in place. What happens if I just let go of it? Well, and let's ignore gravity for right now. Let's ignore gravity for this analysis. Well, it's going to feel this electric force, and it's going to be free to move, and it's going to go boom. It's going to shoot off to the right and try to hit this plate over here. Well, it's going to give the object kinetic energy. Well, if this force is transferring energy into this moving charge as it goes to the right, that means there has to be energy stored up somehow. I mean, you can't create or destroy energy. All you can do is transfer it from one system into another system, or from one object into another object. So what you can think of this is this. Let's take a positive charge right here, and it's stuck right here. The field is holding it right there, but I'm going to force it to move. I'm going to do work. I'm going to apply a force to it, and I'm going to force this positive charge to move across this electric field. Well, here I go. Okay, so I applied a force. I'm from outside of this system, and I'm going to apply a force to this charge, and I'm going to go. Well, I transferred energy from my arm into this guy. And how much work did I do? How much work did I do? Well, it's the force that I had to apply times the distance between times, well, work is F dot delta R, right? Okay, so let's just say, well, now the force that I'm going to apply to move this across at a constant velocity across like this is just, all I have to do is be the tiniest little bit bigger than that electric force. Well, in fact, if I'm moving at constant velocity, it's going to be exactly equal, but in the opposite direction. So the force I'm applying is to the left, and that force is going to be equal to Q times E. Okay, now, but in the opposite direction. Well, let's not worry about direction too much right now. But I'm going to move it across like this. And this delta R, I'm just going to call this D, and that's going to be the distance between the plates. Now that let's not worry about the negative sign for right now. I have done work. I have transferred energy, and now I got to hold it there. I got to hold that positive charge there. Because if I let go of it, what's going to happen? It's going to go ving. It's going to move across like that because it's in an electric field that's pushing on it. So if I move it over here, I'd say, okay, I transferred energy into this system. I did work. I pushed it over here. But now the electric field can do work on this. And if I release it, it's going to give it back to me as kinetic energy. This is just like gravity, right? Let's think about gravity over here. Here's the ground. There's a rock on the ground. Well, what do? I lift the rock up. See, we got the force of gravity here, but I apply a force to it that's equal to that gravity and just lift it up to this height. And if I have to hold it there, right? And if I don't hold it there, if I release it, I'm going to get all that work that I put into lifting it is going to come back as kinetic energy as this thing falls until it hits the ground. Same thing is happening with electric force. Okay, this electric force is going to be able to do work on the charge. Now we're going to call this U sub E. This is EL, I guess EL for electricity. I'll just spell it. U sub electrical. Electrical potential energy. And it's the work that the electric field can do on a charge because that charge is in an electric field. And it's equal to Q E times D. Okay? Well, we could do that, and this is going to be joules. Let's take a look at the units here. What units does this charge have? Q. Coulombs. What are the units for electric field? Newtons per coulomb. What are the units for, the distance across the plates, or my displacement across the plates? Meters. Well, notice the coulombs cancels, and a Newton times a meter is equal to a joule. So anyway, so this is the equation that we're not going to use very much. Okay, this is the electric potential energy that this little charge has right in there. Now we're going to do something that we don't do with gravity. Well, and later on when if you study more physics, like in your junior or senior year of being a physics major, you actually study this thing called gravitational potential. But let's not worry about that right now. We are going to worry about electric potential. Let me write it down here. Electric potential. It's when I take the electric potential energy, and I'm just going to I'll put a capital E in there. Electric potential energy, and I'm going to divide it by my test charge, Q. Well, what does that equal? That's equal to Q E times D. Remember, this displacement is a vector as well. I'm going to just not worry about that though, because I'm just going to say the electric field and the distance across the plates are in the same direction. Okay, and then so the electric potential energy is the charge times the field times the distance across the plates. And then I'm going to divide that by Q. Now this is by definition. This is how I define electric potential. It's the amount of energy stored on that little charge divided by its charge. Well, its charge cancels out. And I get electric potential. Now, what variable do we use for electric potential? This is a big deal. We're going to call it, for right now, and this is what the book does. The book is a little Yeah, it's pretty good. I would definitely recommend that you read the book as well as listen to this lecture. Okay, so we're going to call it delta V. This is not velocity. This is a capital V, delta V. We're going to define that by definition is the change in electric potential energy per unit charge. Right? I mean, think about it. If I let go of this charge up here and it slides across here, it's losing potential energy. And I can say, well, what's the difference between the potential energy here and here? That would be delta U. And then I'm going to divide it by the charge on my object. And this, by definition, is called potential difference, capital P, difference, or it's also called electric potential. And sometimes we even call it voltage, or a change in voltage, or that's where the V comes from. Now, I'm sorry. I am going to apologize on the behalf of the physics community. I am going to apologize because electric potential is the worst named thing in physics because there are so many different names for it. There's electric potential, potential difference, voltage. There's even one, and we watched this in. No, that's the recording. That's the recording. You are not free to leave yet. The bell rang while I'm recording this. Okay, this is EMF, electromotive force, which they use sometimes the letter E to represent. It's got a lot of different names, and that's because when they were figuring all this stuff out, they were looking at the same thing with different points of view, and they called it different things, and it's really annoying. I'm sorry. Sometimes I will say electric potential or potential difference or voltage or EMF. Right now, I'm mainly going to talk about electric potential. That's the one I'm going to use the most. Notice what's different here is I don't say electric potential energy. Electric potential energy is when I don't divide by Q. That's just the delta U right there. But when I divide by Q, for some reason, we just drop the word energy and just call it now electric potential. Now you know this as voltage. And voltage is measured in, well, let's take a look at the units here. What are the units for this? The units for this are joules. And the units for this are coulombs. And what's a joule per coulomb called? It's called a volt. Oh, I keep doing this crooked. I don't know why I'm being crooked today. So this is a volt. It's a joule of energy, of potential energy in an electric field per coulomb of charge that you move across that electric field. And so that's how you'll see voltage. That's the definition of voltage. And this is the voltage that you're familiar with from everyday life. Like if you go out and buy a 9-volt battery, that means that it will deliver 9 joules of energy for every coulomb of charge that moves through it. Okay, that's what that means. And we're going to talk about DC circuits and so on later on, where that's how we look at it. But right now we're dealing with electrostatics. We're dealing with electric fields. And if you place a positive charge in an electric field, you're measuring how much work per unit charge that electric field will do on that charge. All right, I think I'm getting, I'm babbling a little bit. So this has gone on long enough, but here's what I'd like you to do, class. I would like you to do the 2 example problems in the book. This is part of the assignment. And I'll go through the example with you right now. Here's your book. And let me zoom in a little bit. Take your books out. This is on page 491. And so here we've got two parallel plates are given opposite charges. A voltmeter measures the electric potential difference. There's that word electric potential, and then sometimes they'll put the word difference there, to be 60 volts or 60 joules per coulomb of potential difference between here and here. The plates are 3 centimeters apart. What is the magnitude of the electric field between them? Okay, so what do we know? Well, we know, what's given. I like to use the word given. Well, we know what delta V is. Delta V is 60 volts. And we know that what distance it has to travel. It's 0.030 meters, right? It said 3 centimeters, which is 0.03 meters. And what are we trying to find? It says, what is the electric field E? What is E? What is the electric field? So, well, we use our basic equation. And I would say our basic equation that relates the potential difference and, well, actually I didn't really get to that, did I? Delta V is equal to the electric field times the distance, the strength of the electric field times the distance. Okay, so here's our electric field. And let's take a look at the units here. This is newtons per coulomb times meters. Newton meter is a volt. Newton meter is a joule. Joule per coulomb is a volt. So this is the equation that relates the potential difference between the plates, the electric field between the plates, and how far apart the plates are from each other. And that's what you're using here. They solve it for the electric field. Oh my gosh, like it was visible in there. Yeah, it was. Okay. Sorry, I'm not in a classroom, so I have to, I am in my classroom, but there's no students here. I'm by myself, so anyway. So you just take, 60 volts divided by 0.3 meters, and then you, that'll be the electric field. And look at the units here. You have a joule per coulomb meter, but a joule is a newton meter, so you end up with newtons per coulomb. 2 times 10 to the 2,000 newtons of force per coulomb of charge in between. So what this means, if I put a coulomb of charge in between those plates, it's going to feel 2,000 newtons of force. That's what you have discovered by doing that calculation. And then I'd like you to do given, find, and solve, and solve this other example problem. And this is on page 492, right, just the next page. And it's the same kind of thing. But here you're given the strength of the electric field, the distance between the plates, and the charge on your little test charge there. And what you want to know is what's the voltage difference across these plates? And how much work do you need to do? Oh geez. Pay no attention to that. How much work do you need to do? It says, what work will you do to move the charge equal to that of 1 proton from the negative to the positive plate? Well, that's the charge of a proton right here. So we're going to figure out how much work I need to do. And so it's done very nicely for you here in the book. So go through that and do your best to understand it. All right, that's it. I talked too long as usual. But that should get you started on electric potential. Let me zoom all the way out here. And, well, good luck to all of you. I hope you get this assignment done. That is all.